In this video, we are going to compare the reactivity of different carboxylic acid derivative, that is amide, ester, anhydride and acid halide. So what is carboxylic acid derivative? We know that the structure of carboxylic acid can be written like this, RCOOH. So a carboxylic acid derivative is the one in which the OH group of this carboxylic acid is replaced by another group. So it can be write like this, RCOZ, where Z can be NH2 in case of amide, then OR 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 dash in case of ester, then OCOR dash in case of anhydride, then X in case of acid halide. X is any halogen. So now we are going to see the general reactions of this acid halide, acid derivative. Okay. So the general structure of this acid halide can be written like this, R, not acid halide, acid derivative, RCOZ. Okay. Here, due to the electronegativity difference between this carbon and this oxygen, the bonded pair of electron will slightly shifted towards this oxygen. So this oxygen will have a slight negative charge and this carbon will have a slight positive charge. So a nucleophile is approaching towards this carbonyl carbon, and this electron will shift towards here and Z will leave. Then we have R, C double bond O, Nu after the removal of this Z. So let us have the general mechanism. So this reaction is taking place in two steps. Step 1 is the addition of this nucleophile. R, C double bond O, Z. Nucleophile is attacking. Nucleophile will have a negative charge or lone pair. It will attack at carbonyl carbon and this electron will shift towards here. And we have an intermediate like this, R, C, O minus. Then here one Z will be there. Then here this nucleophile will be there. Okay, so an intermediate is formed in step 1. This is step 1. Then step 2. Step 2 is this intermediate. In this intermediate, Z leave as Z minus, and this O minus, the negative charge of this O minus is come here and form the new double bond. So we have, this is a bond of, okay, not double bond, R, C double bond O, Nu. So yes, plus Z minus. Okay. So now consider if Z, so difference in reactivity of different carboxylic acid derivative, where Z is NH2 in amide, then OR in ester, then OCOR in anhydride, and X in acid halide. If you look at this group, you can see that in each case the attaching atom have at least one lone pair of electron. In case of oxygen there are 2 lone pair of electron. In case of halogen there are 3 lone pair of electron. So in any case there is at least one lone pair of electron. So since this lone pair of electron is in connection with this carbonyl group, it can be delocalized like this. That is, the resonance structure of any carboxylic acid derivative can be written like this. That is, the group Z will contain a lone pair of electron. So this may shift towards here, then we have a structure like this R, C, O minus, here Z, here plus charge. Then the lone pair of electron is coming here. Then we have R, C, double bond Z plus, then here O minus. Okay, so we wrote 3 resonating structures, 1, 2 and 3. Okay, if you look at structure 2, it is favorable for this reaction. That is, if this carbonyl carbon have a positive charge, a greater positive charge, it is very easy to approach the new nucleophile towards this carbonyl carbon and form this tetrahedral intermediate. But presence of the third resonating structure, that is structure 3, here the positive charge on Z. So it is very difficult for this kind of structure to approach this nucleophile. So it is not favorable, or if our carboxylic acid derivative is preferred to form this kind of resonating structure, it is very less reactive. So this structure, the contribution of this structure towards the resonance hybrid depends upon the basicity of this Z group. That is, when this lone pair of electron is donated easily, it is the stable. This will be a stable structure. So, in short, we can see that the relative reactivity of this different carboxylic acid derivative depends on 2 factors, that is resonance and leaving ability of this leaving group Z, leaving ability. So how this resonance is influencing this reaction? That is, when this structure is stable, that is the basicity of this Z is very high, it is easy to donate its electron to form a double bond. So this structure will be have a greater contribution. So it will not provide an easy attack of this reaction. So this is the first step, which is rate determining step. So this is the slowest step, or rate determining step. So it is very difficult to attack at this position when this third resonating structure is contributing more. So if we compare these compounds, or different carboxylic acid derivative, the greater basicity is for NH2. So the order of basicity is NH2 is greater than, NH2 minus is greater than, then RO minus, then RCOO minus, then X minus. So lower the basicity of Z, lower is the resonance stabilization achieved. That is, the greater stabilization will be for amide and least stabilization will be for this X minus. So due to this greater stabilization and hence the contribution of greater structure like this, the reactivity will be poor for amide, and the order will be reverse. That is, reactivity is more for X than this, and then this. Then the lower basicity of Z, the greater is the reactivity of the molecule towards the nucleophile, which means that the step 1 of the mechanism for the reaction involving nucleophilic attack, the formation of tetrahedral intermediate, the reactivity order will be what? Amide is very much less than ester, then anhydride, then acid halide. Okay, I will tell once more. Greater the basicity of the leaving group, what happens? Not leaving, greater the basicity of this Z, greater will be contribution of resonance structure 3, and hence it is very difficult to attack it here. So lesser the basicity, greater will be the reactivity. So more reactive will be acid halide. So let us check the next point, leaving ability. So better the leaving group, that is easier it is this step, that is the second step will be the removal of the Z as Z minus. So the group which is left very easily will react more. So among these groups, better leaving group will be X minus. So X minus is a very good leaving group. Then the next one is RCOO minus, then RO minus, then NH2 minus. So better the leaving group, greater will be reactivity. So the greater reactivity is for acid halide. So in short, we can see that the overall order will be amide, least reactive is amide, then ester, then anhydride, then acid halide. Okay, so let us draw the structure also. Amide is RCONH2, ester is RCOOR dash, anhydride is RCOO COR dash, then acid halide is RC double bond O X. Okay, so you should remember 2 points. One is resonance, other is leaving ability. So more resonantly stabilized structure is this. So hence the reactivity will be less. So leaving ability, X is the good leaving group. So the reactivity is greater for that contain good leaving group. So overall reactivity is this.